So we've done central limit theorem for means. Now let's do confidence interval for means. So just like we did with proportions, in reality, we actually do not know what the true mean is. So we try to estimate it using x bar. So I don't not know what mu is. This is, that's kind of ugly. I don't know what mu is. So I'm going to try to estimate it with the statistic x bar. Now, if I constantly get different samples, I will have different types of x bar, different sample means. So it would be nice to have a interval where I can try to figure out that, okay, well, it's somewhere between this and this. So we're going to do kind of the same thing. So I gave a little blurb here of what exactly we're doing. So we don't know what mu is or where it's located. So we estimate it with x bar, and we hope that it will give us a range of values. Or we want a range of values where mu can be found. So also the thing about the sample proportion was that the standard deviation was just square root of p1 minus p divided by n, the standard error. So it all depended on p. Now here, for means, we have two different things. We also have a standard deviation, sigma. Okay, so we actually don't know what mu is, and we also don't know what sigma is. So one way that we can fix this is to estimate it with s sub x, which is what we did kind of like in the first day of classes. This is how we found that we're given a set of data, and we were able to find the standard deviation the long way, or using the calculator. So we don't know what that is, so we're going to estimate that. So basically, the confidence interval formula is this. So x bar plus or minus t n minus 1 s over square root of n. Here, x bar is my estimate. So here's my estimate. This s is basically my s sub x, my standard deviation. And then this n is just my sample size. If you want to know where this formula came from, I can show you in class, and I can go ahead and derive it for you. Now, one thing that's very different about this confidence interval formula was that before, the confidence interval formula for sample proportion was p hat plus or minus z star square root of p hat 1 minus p hat over n. Okay, so notice that we still have that over n, the square root of n stuff. We have the estimator, so we still have that. But the only difference here is that here we have a z star, which I kind of gave to you. There's 3 that we will use in class. The 1.645, 1.96, etc., etc. Now, in this case, we have a t n minus 1. Now, this t is going to be a completely new distribution. So let me explain to you, before we use this formula, what that distribution is. So this is what we call the student t distribution. So student t distribution is a continuous distribution used to estimate the mean of a normally distributed population where the sample size is small and the population standard deviation is unknown. So because I didn't know what the population standard deviation was, which was sigma, I didn't know what that was, and I estimated it with s sub x, then I can no longer assume that everything's going to be normal. Now it's going to follow a completely different distribution called student t. There's a reason why it's called student t. You don't need to know the history behind it. But basically, the thing about the student t distribution is that everything is just a normal curve. So I put here some features. It looks just like a normal distribution, but it has fatter tails. So if you see, we have different normal distributions or lookalikes of normal distributions, and I'll tell you what that is right now. So student t is very similar to normal. It has a parameter called degrees of freedom, and this degrees of freedom is found by taking n minus 1. And we use a t table to find t n minus 1, and you can view it on Blackboard. If you go on Blackboard and you click on tables or t tables, it'll be right there. So degrees of freedom, you can see that there's differences in degrees of freedom here. And basically, as the degrees of freedom increase, this starts to look more, or this tends to go to a actual standard normal distribution. So you need to know how to use this formula. Before we know how to use this formula, let's try to figure out some t n minus 1s. Okay, so let's do this quick problem. So use the t-table to find Tn minus 1. Now the t-table is going to look something like this. So if you go into Blackboard, this is what kind of the t-table looks like. So one of the things that you're going to be looking at for the t-table is that you're going to be looking at the bottom portion. The bottom portion is going to tell you what the confidence level is, what kind of confidence I want. And then this first column is what we're going to call my degrees of freedom. Remember, degrees of freedom is equal to n minus 1. So we're going to take the sample size subtracted by 1. And then we're going to kind of match everything up. So let's do the first problem. So what we want to do, we want to find Tn minus 1 when n equals 10, and we want a 95% confidence interval. So remember, the first step that we want to do is find degrees of freedom. That's the first step. First, find df. Okay, and then use t-table. Okay, those are basically the steps. So first, let's find our df. Now, degrees of freedom is n minus 1. And in this case, it's equal to 10. 10 minus 1, which gives me 9. Okay, so n equals 9, and this df is equal to 9. So what is Tn minus 1? Okay, well, df is equal to 9, and we want a 95% confidence. So we're going to go to the t-table. We're going to look for degrees of freedom equal to 9. Okay, so here's 9. So basically, these are all the values of t. Okay, all of these things. Now, which one do we want? Because we don't want all of them. We only want one of them. So we're going to go look down on the confidence level. And since we want a 95% confidence, we're going to kind of match everything up. Okay, and the one that matches up is this one, 2.262. So Tn minus 1 is going to be 2.262. So this is going to be 2.262. And that's it. That's how you find Tn minus 1. Okay, so now let's do the next two. So now we want to figure out what Tn minus 1 is going to be when n equals 21 and at a 99% confidence. So first, let's find degrees of freedom. Take n minus 1. So we're going to take 21 minus 1 is going to give me 20. Okay, so Tn minus 1, what is that going to be? So we're going to look for 20 at a 99% confidence. So I'm going to go back. So here's 20. 20 is going to be right here. So it's going to be one of these rows at a 99% confidence. Here's 99. Okay, I'm going to go up. Okay, so here's going to be my answer, 2.845. Okay, so it's going to be 2.845. Okay. All right, and then the last one at n equals 43 at 98% confidence. So df, is equal to n minus 1. So we're going to take 43 minus 1 is equal to 42. Okay, so what would Tn minus 1 be? Okay, so at 42, okay, so we're going to look at our t-table at 42. Now notice here that it's not possible for me to get every single degree of freedom, but we know that 42 is somewhere between 60 and 40. Now what we're going to do, if the number is not here, we're just going to estimate it and look for the number that's closest. So here in this case, 42 is closer to 40. We want a 98%. So we're just going to pretend that this is going to be it. So just go ahead and just estimate. And the answer is just going to be 2.423. 2.4. Wait, what? What was the answer? 2.423. 23. Okay, so if the degrees of freedom is not there, just go ahead and estimate it. Okay, so hopefully this helped to find the value of Tn minus 1, and then in the next video, I'm going to go ahead and do a problem.